Okay, so we want to calculate surface area, but of a function, a surface that is described parametrically. So the way you describe a surface parametrically is to take a vector function r of u and v, and have each component be a different maybe the same, be a multivariable function of u and v. In the special case where u is between two constants a and b, and v is between two constants c and d. The formula to calculate the area is here. What you do is you take the u partial derivative of that vector function and cross it with the v partial derivative of that vector function. That gives you a vector, and then you take the magnitude of that vector, and then that gives you a function, and then you integrate that function over the rectangular region where u's go between a and b and v's go between c and d. Where the formula comes from is these guys, r sub u and r sub v, are vectors. When you cross two vectors, you get another vector that is orthogonal to both of them. When you take the magnitude of a cross product, what you're getting is a parallelogram area. So here's a parallelogram area, which is used to approximate the surface area. The smaller the change in u and change in v will be, the better this approximation will be to the actual surface area. And then we add up a bunch of these, and that's how we end up with this double integral. We add them up over the changes in u's and over the changes in v's, and what we end up with is a double integral. So now let's go calculate for a particular example. We have a sawed-off sphere, a sphere that's cut off by the cone. Z equals the root of x squared plus y squared. The sphere has a radius of root 2. And what we want is the lower portion of surface area. So we need to parameterize. It's a sphere, surface area of a sphere, where the rho is constant. If you look at the equation x squared plus y squared plus z squared, that's what rho squared is. So rho squared is 2, and so rho is root 2. Now we can go and replace the rho's in the formula with root 2's, and this would be our parameterization. When you parameterize, you come up with what x is as a function of two variables, what y is as a function of two variables, and what z is a function of two variables. And this is what we end up with: root 2 sine phi cosine theta for x, root 2 sine phi sine theta for y, root 2 cosine phi for z. And so now we want to calculate the surface area by finding these partial derivatives, vectors, and crossing them. We've got to make this vector r of the made up of these guys as their components. Find these partial derivatives, cross them, and then find the magnitude. And we have to figure out the bounds on phi and the bounds on theta. When the cone intersects the sphere, we have the sphere with the equation rho equals root 2. We have the cone with the equation z equals the root of x squared plus y squared. And so we convert by trading in everything for spherical. We have that z is rho cosine phi, and the root of x squared plus y squared is r, which is rho sine phi. So rho cosine phi is rho sine phi, but we know what rho is. Rho is root 2. Dividing by cosine phi and dividing by root 2, we end up with the tangent of phi is 1, or sine of phi is cosine phi. So phi better be pi over 4. So that's where phi starts at. But phi then goes all the way down to pi. We're talking about the lower surface areas part. So we start at pi over 4, but we end at pi for phi, the negative z-axis. And then we allow theta to be, of course, anything from 0 to 2 pi. So now let's take some partials. We're going to take the partial derivative of this with respect to phi. So we have a sine phi, which becomes a cosine phi. We have a sine phi, which becomes a cosine phi. And then this cosine phi becomes a negative sine phi. So that's our phi partial. Our theta partial, the cosine theta turns to a negative sine theta. The sine theta changes to a cosine theta. And there'll be 0 because there's no thetas in this last component. And now what we need to do is cross these two vectors to find, and then later find the magnitude of that. And once we cross them, we'll then integrate as phi goes from pi over 4 to pi, and theta goes from 0 to 2 pi. Once we cross them, we'll take the magnitude and integrate that. And that'll give us our surface area. So let's go get the cross product, I, j, and k. The r sub phi is the second row, the r sub theta is the third row, and we're going to cross out i's column and i's row and do this subdeterminant here. We get 0 minus a negative, this product here, and so we get plus a root 2 and root 2 is 2, and we have sine squared phi cosine theta from here. Then we cross out j's column and j's row. We end up with a 0 again and a negative because there's 3 negatives here, but actually there's a 4th negative. So what happens is cross out j's column, cross out j's row, we get the 0 minus 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 is a negative 2. Root 2 and root 2 is 2. Sine phi is sine squared phi, and then the sine of theta. And remember that the j component gets a negative on it, so there's actually 4 negatives floating around. We end up with a positive value there. And then finally we cross out k's column and k's row, and we end up with 2 sine phi cosine squared, and then plus 2 sine phi cosine phi sine squared. And the cosine squared plus sine squared you get left over when you factor out the 2 sine phi cosine phi. Alright, great. So this is going to be a 1. This is going to be a 2 sine squared phi sine theta. We have the cross product. Great. What are we to do with this? We're to find its magnitude. The magnitude of the cross product is found by taking the square root of squaring each component. So you square the I component, you get 4 sine to the 4th cosine squared, 4 sine to the 4th sine squared, 4 sine squared cosine squared is what you end up with. And you end up with these 4 sine to the 4th can come out of these first two terms and leave it with sine squared plus cosine squared. So that's just going to be a 1. So now you have a 4 sine 4th, and this third term here, 4 sine squared, all this is on phi, cosine squared on phi. And now we can factor out of here 4 sine squared of phi. When we take a 4 sine squared of phi out, we'll be left with another sine squared of phi, and then here conveniently a cosine squared of phi, and these guys combine to give you 1. And so we take the root of each of these. This is a nice perfect square. We get 2 times the sine of phi is the cross product magnitude. And that goes into the formula. And we integrate this with the bounds on phi and theta. So we have 2 sine phi, which we have to integrate. That'll give us negative 2 cosine phi. We have to put the pi in and the pi over 4 in. We put the pi in, we're talking about the cosine of pi with the negative 2 on it. And then we subtract what we get by plugging in the pi over 4, the cosine of pi over 4 with the negative 2 on it. Okay. And then the other guy doesn't have any thetas in it, so we can just integrate that separately and then multiply the two parts together. The cosine of pi is negative 1. And the cosine of pi over 4 is root 2 over 2. So what's going to happen is this guy's going to be a 2. And this guy is going to be a positive root 2. And this 2 pi comes from this part here on theta. And so that's our answer.